Welcome to the Moscow Telecommunication Seminar. Our today's speaker is Aleksey Kureev. Aleksey Kureev obtained his master's degree in applied mathematics and physics in Moscow Institute of Physics and Technology in 2017. Currently, he is a researcher in wireless networks lab at the IIT Piras and researcher at the Laboratory of Telecommunication Systems in the High School of Economics. Also, he is a PhD student at MIPT. Today, he will tell us about non-orthogonal multiple access and its application in Wi-Fi. Aleksey, the floor is yours.
Hello, everyone. So, yes, as Vyacheslav said, today I'm going to tell you about non-orthogonal multiple access, its fundamentals and application in Wi-Fi. So why did I choose Wi-Fi networks? Because Wi-Fi networks is rapidly growing, and from year to year, the number of devices connected to the Wi-Fi networks grows. By 2026, the number of devices with Wi-Fi 6 support will be increased by 13 billions, and there might be 828 million Wi-Fi hotspots by 2023. So that's why this topic and the application of Wi-Fi networks are quite important. Actually, if we think about non-orthogonal multiple access, we can think about it first. Why do we need to implement this new access technique? And the main idea is to increase the overall spectral efficiency of wireless networks and the achievable data rates of the whole network. And how we can do it in other ways. For example, we can use MIMO. So we can use multiple antennas for transmission and reception. We can use new modulation schemes. For example, we can use in Wi-Fi 7, which is currently in development. There can be 4096 QAM. Of course, we can develop some new channel access methods. And non-orthogonal multiple access is one of them. The main idea of non-orthogonal multiple access, let's say NOMA, is to transmit several devices signals at the same time and frequency using only one antenna. So if we have one antenna transmitter, we can transmit data to several users. And we can do this by separation, power division between multiple users. For example, consider a case of downlink transmission. And in this case, we have an access point and two devices, STA1 and STA2, and STA1 has worse channel conditions than STA2. And we allocate more energy, more power to STA1 transmission. And STA1, because its signal, since signal to STA2 acts as noise. So it's too small for STA1, it even cannot even decode it at all. And if we consider station 2, in this case, station 2 decodes the signal to station 1 at first, and then performs successive interference cancellation. So it reconstructs this signal from dedicated to STA1, subtracts this reconstructed signal from the whole, the received signal at all, and then receives and decodes the signal dedicated to itself. And this is the example of non-orthogonal multiple access in downlink. Of course, it can be used in uplink too. And if we consider uplink transmission, here, this signal superposition occurs over the air because STA1 and STA2 transmits just its own signals. And AP does successive interference cancellation to decode frame from STA2 at first, and then frame from STA1. So here, in this case, opposite to the previous one, where the signal power dedicated to STA2 has less energy comparing to the signal to the STA1. Here we have the opposite case. The energy from STA2 is higher than the energy that on the reception from the STA1, because the distance is higher here. So here we save the same notation. We have NOMA frame transmission in uplink and in downlink. And if we consider an uplink transmission, we have a primary frame which comes from STA1, and we have secondary frame which comes from STA2. And this is the common notation for uplink and downlink transmission. And in my talk, I will try to tell you about the fundamentals of downlink NOMA at first. And I will describe you a common view how NOMA might be implemented in a network, in wireless networks. Then I will describe you some implementation issues and implementation features of NOMA in Wi-Fi. And then we can go to uplink NOMA, and we will describe some implementation issues of uplink NOMA in Wi-Fi. So let's start. Fundamentals of downlink NOMA. To start this, we need to at first understand how actually the signal superposition works on the transmitter. If we consider an off-jam signal, and we have an access point which is trying to transmit some data to STA1 and STA2, we have this sort of NOMA frame, which is a combination of primary and secondary frame, and each of them symbol consists of subcarriers. And actually, each signal in each subcarrier can be represented using the IQ samples. And superposition works the follows. Each IQ sample in frequency domain of primary frame multiplies by square root of 1 minus alpha. Alpha is scaling factor, which represents the division of power, the power ratio between primary frame and secondary frame. And each IQ sample in frequency domain of secondary frame multiplies by square root of alpha. And the resultant signal will be the combination of these two constellation points, which is scaled by some function from alpha, and we see the NOMA signal. And if we consider a case of NOMA reception, the far station considers signal to STA2 as noise, and the received constellation will be smeared by the noise, and we see some like this very, very smeared red point, which corresponds to multiple received points that are received to the access point from this constellation. And if the noise is not too high, this station 1 can decode this signal and understand that there is even this point. For example, if QPSK was transmitted, this point from QPSK alphabet is decoded here. A near station has high SNR and can distinguish its own signal here. And that's why we can do this successful inference constellation procedure on the receiver part. What is the drawbacks of superposition coding? So consider a case where we want to multiplex two QPSK signals. Here we have this combination of NOMA signal, which corresponds to which is the combination of two QPSK signals. These black colored points correspond to bits that corresponds to STA1, and these red colored numbers corresponds to the bits for STA2. If we consider in detail this constellation, we see that the Hamming distance between neighbor constellation points can be higher than 1. For example, here you see that here is 0011 and here is 0110. And if the error occurs, we will receive the error in 2 bits instead of 1, which is usually used in Wi-Fi. So the resultant constellation is not great coded. The solution for this case is the usage of symmetric superposition coding. The idea of the symmetric superposition coding as follows. So we construct the constellation, the resultant constellation of NOMA frame, the same way as the Hamming distance between neighbor points is always 1. You see here, we consider these two neighbor points as in previous case, and we see that it is 0, 0, 0, 0, and here is 0, 1, 0, 0. So I have a quick question to audience. Does anybody see my mouse movements or not?
Yeah, we can see.
Oh, great. And this is another case. So what we can do more, how we can build a more robust signal constellation. If we just view in details to the actual constellation point, the resultant constellation point in the receiver, we can see this. So this the resultant constellation on the receiver, and we see that we see not only smear caused by additive white Gaussian noise, which is commonly considered in some theoretical works of NOMA. We can see this circular smearing, which corresponds to the phase noise. And the reason of the phase noise is as follows. So the hardware impairments, they can cause this phase noise. For example, the inequality of oscillators frequencies on the transmitter and the receiver sides. Of course, again, so AWGN, the Gaussian noise during the phase recovery stage, because each of them symbol in Wi-Fi, for example, or another case, we do some phase correction, and it can be not so right, and there might be some problems here too, and Doppler shift. Doppler shift is another problem, because if we have movements in the space, or transmitter or receiver moves, there is a Doppler shift in frequency between transmitter and receiver, and it can also cause the phase noise. And the way to beat this phase noise, or just decrease the influence of the phase noise, is to rotate the constellation of the secondary frame, which is used in downlink transmission. Here we see an example of combination of BPSK and 16QAM with no rotation, and we see that phase noise destructs the signal, and these constellation points are smeared, and we see the constellation of BP combination, the same combination of constellations with a 45 degrees rotation. The idea here is to make the direction of the, so the idea of the phase rotation, or the constellation rotation, is to change the direction of phase noise influence and thus make the constellation more robust for reception. And if we consider the implementation issues of NOMA in Wi-Fi, so all these techniques that I mentioned before, like using symmetric superposition coding instead of usual superposition coding and the constellation rotation, is applicable to any technology that is going to use NOMA or NOMA in downlink. And now we go to implementation of NOMA in Wi-Fi. So in our lab, we built a prototype of non-orthogonal multiple access in Wi-Fi in downlink. And for this, we use the 802.11 application framework from National Instruments for LabVIEW communications, and software-defined radio and IUSRP RIO 2944R. So this is quite powerful device, quite powerful SDR, because it can process data in 80 megahertz band, and it has FPGA inside, and that's why it can process data even inside this device without any transmission of IQ samples to the PC to make some computations here. So we use this device to build our prototype. And in our prototype, we implement one device, one USRP as a Wi-Fi access point with a NOMA transmitter inside, one device which acts as a NOMA receiver, like STA2 in our previous notation, and it's also USRP, and some legacy device. In our example, it's MacBook. And this is the photo of this device and how we implement the receiver. Probably the main and the most interesting part of the NOMA is the NOMA receiver. If we consider the state-of-art scheme where we have successive interference cancellation to decode the primary and secondary frame, while trying to implement it, we face several problems which are very important, and without solving them, we cannot even implement it at all in Wi-Fi, especially in Wi-Fi. For example, here you see the standard state-of-art processing chain for original Wi-Fi receiver. We see a RIX-IQ processing block, which is corresponded to IQ processing, signal equalization, fast Fourier transform, and so on. We have the modulation, and we have a conversion bits to bytes, and then further it's processing on MAC layer and so on. If we consider the NOMA receiver with SIG, we see that this transmission reception scheme becomes more complicated, more complex, and we see that there is a buffer which a response which is needed for the saving all the received signal, and the longer signal we have, the more IQ samples we need to store in this buffer, and this is the one problem. And the second problem is that we need to, for correct and signal constellation, successive interference constellation, we need to restore all the bits which we received from the original primary frame. We need to reconstruct it to the IQ samples again and subtract it from the buffered signal. And here the great latency. Here we can see the great latency because the overall the duration of signal reception can be higher and twice higher than the original signal reception. And for example, if we want to implement NOMA receiver in Wi-Fi, we understand that we need to receive the signal inside the SIFS interval, a short interframe space interval, actually, this scheme cannot be implemented in real Wi-Fi devices because of the too long signal processing, which can be longer than this short interframe space interval. Another idea of implementation of NOMA receiver is the usage of parallel constellation demapping instead of successive interference constellation. The idea is to process the constellation points in parallel. If the received signal is too high, the SNR is too high, we can demodulate this signal in parallel, and in parallel we can demodulate signal which corresponds to STA1 from primary frame and the signal from secondary frame. And this scheme is simpler. So we don't need to use the buffer to store all this data, all these IQ samples, and we decrease the latency in frame processing. And this scheme allows us to implement NOMA in Wi-Fi, and we implemented actually this scheme in our prototype. And this is the results of our NOMA receiver. So how it sees the combination of constellations from primary secondary frame, and this is the example from QPSK and QPSK modulation, and this example of CAM16 from CAM16. The one thing that I should notice here, that actually in literature, if researchers consider the influence from the secondary frame on the primary frame reception, it usually considers as the additive wide Gaussian noise. So, in other words, these points might look like a big circular point, big round point, without any complex structure inside it. But in practice, you see that the influence should not look like the additive wide Gaussian noise. So this influence is much more complex. And to study this, we conduct some experiments. And we vary the scaling factor alpha, and this scaling factor this scaling factor. From this scaling factor, we can obtain the overall SINR, a signal to noise plus interference ratio, and we can measure frame reception ratio, which is a result of the several NOMA transmissions. And here you see that this is the influence of secondary frame on primary frame reception. And these brown curves corresponds to frames that transmitted without NOMA on NCS0, which uses BPSK, and NCS2, which uses QPSK modulations. And you see that to transmit and to successfully receive these frames, we need much more SINR than if we use NOMA, and we consider this SINR that is caused by secondary frame. And here we see that we can achieve even gain in even 4 decibels or higher of using NOMA instead of actual transmission. So this is the one thing that I should tell you here, that the idea of NOMA is that the influence of a secondary frame is not the same as the influence from additive white Gaussian noise, which is commonly used in papers. So we need to pay attention on it. And if we consider the opposite case of influence of primary frame on secondary frame, we see that this influence that we have this influence too, and it's different. And this frame reception ratio depends not only over the coefficient of alpha of scaling factor, but also it depends on the structure of the constellation of primary frame. So if we want to build the very accurate error model, we need to take into account both constellations, primary and secondary frame. And if we consider the constellation rotation impact, we see that here we have an example of a combination of NCS0 for secondary frame and NCS0 4 and 2 for primary frame. We see here that constellation rotation allows to achieve gain up to 3.5 decibels here. And here you see an example, for example, for green curves, which is combination of QPSK and BPSK. And here we have this constellation, and for this dotted curve, dashed curve, we see that the gain is higher, and the overall frame reception ratio, this curve, turns to left on 3.5 decibels. So while implementing NOMA in downlink, we need always to think about not only to the superposition of several constellations, not only on the energy, but we need to see also to look on the constellation points and the angle of rotation of this constellation. And it can help us to improve the robustness of the signal. And if we go to the NOMA frame structure, so if we want to implement our device, our method, channel access method, or NOMA in Wi-Fi, we need to pay attention not only on file layer perspective, some aspects of file layer, we need to pay attention on MAC layer. And the first step is to develop a NOMA frame structure, which will be suitable not only for NOMA receiver, but to original legacy devices. And here in this case, we use non-orthogonal multiple access only for all data, all ODM symbols, which begins from LSIG. And we use LSTF field, which corresponds to signal synchronization and signal detection, and LLTF field, which are responsible for channel estimation. So we do not change these fields. Actually, we do not use the signal superposition in these fields, but we change the actual power, transmitting power of LLTF field to detect the scaling factor and this stay away. So this decrease in power is needed for receiver to obtain the scaling factor alpha and to decode signals from primary and secondary frame. And if we consider the if we want to compare the performance of NOMA and performance of time division multiple access, which is commonly used in Wi-Fi, so we see that using NOMA, we can decrease the duration of the transmission. So here we see the duration of transmission of data for STA1 and STA2, just using round robin. We transmit the first data to STA1 and then data to STA2, and the overall duration will be T1 plus T2. And the duration of T-NOMA is shorter. And here we can achieve some gains, and we achieve gain NOMA. But actually, it's not so obvious, and this gain is not so obvious because to transmit data in NOMA, we need to decrease the modulation encoding schemes that's used for original transmission. So actually, the overall duration of transmission shortens, but the modulation encoding schemes becomes lower here too, and we need to investigate the impact of NOMA usage. And to do so, we consider an experiment. We use the 6th floor of IITP RAS main office. Our space is static, no man's movement, and we transmit data according to round-robin policy in original Wi-Fi and original TDMA, or we use proportional fair policy for transmit data to STA1 and STA2, and we compare usual TDMA, original TDMA that's used in Wi-Fi, and we consider TDMA plus NOMA. So we transmit data in NOMA, and if we want to serve some user and make the true proportional fair, sometimes TDMA is used. And we achieve the gain by 37% in geometric mean throughput for NOMA, comparing with TDMA proportional fair, and a little bit higher comparing to TDMA round robin. So NOMA is effective technique that can be used for Wi-Fi, especially for single antenna transmission. And you may ask a very important question: so how to use NOMA and MIMA? Because nowadays, MIMA is a very popular technology, which is used in Wi-Fi too. And for this case, we can use joint MIMA plus NOMA. And to do so, the access point does modify beamforming and makes a superposition coding inside each beam. For example, here, we construct two beams. One beam corresponds to STA1, and the second beam corresponds to this group of stations. And we can serve these stations in NOMA, all three of them or pair of them. So it depends on channel conditions. And here, devices use successive interference cancellation if it is needed. And another topic that I want to cover is uplink NOMA. As I said, in uplink NOMA, the station, so the superposition coding occurs over the air because signal multiplex due to the interference and so on. And we see that it is very difficult to implement just even a simple Wi-Fi NOMA in uplink because of the difference between channels in STA2 and STA1. Here you see this figure, and you see that STA2 has channel H2 and STA1 use channel H1. And if we just use a very simple superposition of these two signals, they overlaps in time and frequency. The access point receives here LLTF field, which will be common for both stations, STA1 and STA2. And usually, this field is used for channel equalization in access point or just in all Wi-Fi receiver. And here, the received signal Y, which this device receives from this field, is the sum of the signals which are received from STA2, H1 multiplied by X, and X is the LLTF signal, and signal from STA2, and some noise. And when access point wants to estimate the channel to do the further equalization, this channel is a combination of the channels from STA1 and the STA2. So this H is the combination of H1 and H2. And to decode primary and secondary frame, independently and of course accurately the access point or all NOMA receivers in uplink, they need to estimate H1 and H2 independently. And this is the main problem of uplink NOMA. And in all technologies that tries to implement NOMA, for example, in LTE or sorry, in 5G, so there might be a signal, just some division between signals which corresponded to estimation of H1 and H2. And without it, we cannot solve, we cannot implement access uplink NOMA, even in Wi-Fi 2. So, and now we are currently developing some techniques that are corresponded to uplink NOMA in Wi-Fi. And I guess after several times, I will describe you these techniques when we achieve great results here. So if I want to conclude here my talk. NOMA is an opportunistic technology that can improve spectral efficiency of wireless networks. And we show that it can improve the geometric mean throughput, for example, for Wi-Fi networks with single antenna transmitter. And actually, symmetric superposition coding and cancellation rotation improves the transmission robustness. And it is I advise to use these techniques instead of simple superposition coding. And if we want to implement the NOMA receiver, we need to use the parallel constellation demapping because it decreases the complexity of NOMA receiver. And to implement uplink NOMA, it is important to estimate the channels independently. And by the channels, I consider even not only the channel characteristics, but only the phase. So we need to separate the pilot signals and all the pilot signals that are corresponded for several devices. And that's, I guess, all from my side. I will be glad to answer for some questions. Thank you for your attention.
Okay, can you hear me?
Yes.
Thank you for the interesting presentation. I have a question about successive interference cancellation. You've mentioned that you used and implemented parallel interference cancellation, parallel decoding. So you decode the signal to belong to the first and the second user in parallel. But in uplink NOMA, I think there will be problems to do that because the channel is not the same for the first and second user. So the only algorithm that can be used here is to first decode one of the signals and then encode it again and then subtract one signal from another, or there are some other methods which are maybe more efficient and not increase so highly the delay.
So thank you for your question. Actually, now we are facing some, we are trying to implement uplink NOMA receiver to make it. And we modify the parallel constellation demapping technique for this case. And to do so, we previously separate the channel estimations from both signals. So my answer is as follows. If you can estimate the channels independently, you can do the parallel constellation demapping. It will be more complex, but not so serious. So it not be so high. Actually, I cannot present you this result because we haven't implemented yet. So when we implement it, I will describe you this technique in details.
And can you maybe recommend any paper that you use or it's your know-how? Are there any papers on this method?
About parallel constellation demapping?
For uplink, yes.
Actually, it's our know-how. So that's all.
Okay, so you'll be the first.
I hope
that's
so.
Because it's very interesting is how to do that, how to map mixture of signals which have different channels. Okay, thank you.
So I received another one question from Dmitry Kadamsev.
Sorry, can I interrupt to continue the question from the Andrei? Maybe it would be beneficial to show maybe more detail on how the parallel constellation demapping works. So could you please explain it in more detail? Because I wonder if we still need to subtract signal and decode the initial signal. So could you please explain?
Yep. So actually, if we consider parallel constellation demapping, so this scheme, the idea of parallel constellation demapping is to have a general view on the whole signal constellation. For example, consider a very simple transmission of a very simple constellation, for example, 16 QAM. If we consider 16 QAM in original Wi-Fi receiver, we understand the whole points here. So we can detect the whole points of 16 QAM and denote and make a representation of each point to some sequence of bits. The parallel constellation demapping works in the same way, but the idea of this is to construct this general constellation and make a general view to the whole constellation. So the NOMA receiver with parallel constellation demapping, it detects the whole points at the same time, and just detect, for example, this point, but understand that this point corresponds for a sequence of 4 bits, and the first half of the sequence corresponds to the primary frame, and the second part corresponds to secondary frame.
Yeah, but you consider here that the channel is the same.
Yes, and if we consider the downlink transmission, the channel is the same.
Yes, and how to do that in uplink?
In uplink, so you need to do some transformation of, you need to, okay, so you need you need to do the step-by-step equalization of these points. Okay, so let me describe in the following way. If we consider the transformation of the channel that channel do on the transmitted constellation, this transformation will be look like some rotation and some decrease in amplitude. Okay, so the effect of the signal is the sort of transformation of this kind of transformation. If we can understand the channels separately, independently from station 1 and station 2 in uplink, we can do this step-by-step transform of this constellation. Like we can at first transform the general constellation, which corresponds to the first for the primary frame, and then we transform the constellation which corresponds to secondary frame. And here we, after this step-by-step equalization, we can obtain the same equalized constellation which corresponds to the NOMA frame, and then do the same parallel constellation demapping.
Oh, sorry, but I don't understand. Maybe it's easy, but I didn't catch it. That you have a mixture of 2 signals, and first to equalize, you multiply by some operator, by some matrix, your signal to equalize for the first signal. But you multiply the mixture of signals, and then if you want to do the second step, you will do it again to the mixture of signals. So how to decouple the first and the second to equalize the first channel for the first signal and the second channel for the second signal.
So, Andrew, I guess I don't know if I have this opportunity. Probably may I describe it to you in some
you mean, yes,
other time, because
separate talk, yeah.
Yes, it's separate talk. It's not a topic of this discussion.
Thank you.
So I received some question in chat from Dmitry. What is it? So does it work efficiently in case of power of UAEs are equal? Yeah. So if we consider the uplink or downlink NOMA transmissions, NOMA is effective when when we have some difference in power, when the channels are different, and if the channels are quite or less equal, or just gains in channels are equal, the usage of NOMA is ineffective. And it becomes effective only if the channels are very well, and we stays on the bound of the signals. For example, the channel is so good, we can use, for example, 256 QAM, but the technology has a restriction of maximum 64 QAM, and thus we can use multiple 64 QAMs instead of, for example, 256. So actually, but the general answer is NOMA is effective when powers are different.
So may I ask the question?
Yep.
The question is quite simple. Does NOMA always a synonym of power domain schemes, or we also have some other techniques for NOMA?
Actually, NOMA is not always a power domain NOMA, and you're right. But in literature, usually the most popular usage of NOMA is power domain NOMA. And here in my presentation, I consider the power domain NOMA. The idea, so you can use other NOMA techniques. So, and the main principle of NOMA, that you broke somehow orthogonality between signals. You can broke in several ways. And here, the most popular technique is power domain. For example, there is a code domain NOMA, and it's another technique too.
Thank you.
So I received another question from Aleksey. Can you clarify why exactly NOMA for MIMA case is not that effective? So if we consider this situation when NOMA plus MIMA, when we want to use NOMA plus MIMA, for example, you have, let me just draw even in live. Just for clarification, I just describe you this case. For example, you have two pairs of devices, STA1 and STA3, and STA2 and STA4. How you can transmit data for them? You can use beamforming, or just use, you can use beamforming for each of these devices and transmit it in TDMA. Or, for example, you can use even MIMA and transmit transmit data for multiple devices in the same time. For example, we construct two streams and transmit data only for STA3 and for STA2. In this case, you divide this transmission in time. So we transmit data first to STA3 and STA2, and then to STA1 and STA4 in common MIMA. And here we can achieve very high gains because of construction of precoding. We can use zero forcing, and then using zero forcing, we can beat the interference between these two streams. If we use a NOMA in several streams, the task becomes more complicated, because transmitting data in several streams, you can make the interference cancellation between the streams between two devices, for example, STA2 and STA3, but there can be a high interference between STA1 and STA4. So zero forcing will work on the two of devices, but instead of four. And that's why NOMA, if we want to use NOMA and MIMA, sometimes we need to pay attention between not only the channel gains, but to the placement of the device itself. And the NOMA becomes effective if we have all devices which are close to the one stream. For example, we have this device here and this device here, and you want to serve them So in MIMA or in MIMA plus NOMA, and in this case, NOMA becomes more effective because here, even if you use MIMA and you use zero forcing because of small number of antennas, there might be interference between several streams. And beamforming, just simple beamforming TDMA transmission takes much time. And in NOMA, you can organize one stream and transmit data in one stream to several users in the same time. And in this case, NOMA becomes effective. For example, if you have a train and you want to transmit data inside the train, so NOMA is effective here.
One more question from my side. Could you summarize, you already mentioned it a bit during your talk. Could you summarize in which technologies NOMA is already used, in which technologies NOMA developers of which technologies are going to use NOMA in near or maybe not so near future, and in which technologies researchers propose to use NOMA. So you talk about that researchers, so you personally propose to use NOMA in Wi-Fi. So what about other technologies, and what about standardization of NOMA in Wi-Fi?
So actually, NOMA is a part of a standard of cellular technologies, and uplink NOMA in 5G is used, and our colleagues from our lab is already studying this topic. As far as I know, there is a downlink NOMA in cellular networks too. It's called MUST. And as far as I know, it's not so frequently used. And actually, it is now used now because of this issue of NOMA plus MIMA. So because base stations usually have many antennas, and it's much simpler now to use only MIMA. And do not make the construction of signal more complicated. But if we go to specification of cellular networks of 5G, we can see this technology too. And if we consider some research, I read some information about LoRa. It's somehow used, but actually I don't know the details. But I see this. And Wi-Fi, but in Wi-Fi, it's not a part of a standard. It's currently developing uplink and downlink, and we present parts of our results in standard committee, and we are trying to make this technology a part of a standard.
Thank you.
Okay, so if there are no any questions, thank you for your attention.
Thank you, Aleksey, for your interesting presentation and for discussion. So thank you all. See you soon at the next seminar. Thank you. Bye.
Bye.